yours.
Thank you very much. Good evening. My name is Limbold Christmas, and yes, I'm one of the co-founders of SENECA, which we're very happy to have established. It's relatively new as a sort of supplementary organization to the Swedish Astronomical Society, which does excellent work in showcasing much of Swedish astronomy. But of course, a large amount of the astronomers in Sweden are international early career astronomers who have located here on shorter term contracts, PhD students and postdocs and such. So the aim is for SENECA, and with this seminar series, is to showcase some of that work, which is why this is in English. Thank you for your patience. And so tonight we have two such speakers. We have Andri Spilker and Adam Rains. Our first speaker is Andri, who has recently defended her PhD at Chalmers University in Sweden. And Andri, if you are able to start sharing your screen and yourself.
Hi.
I'll pass the word to you. We'll have questions at the end. You're more than welcome to put your questions in the chat. And if not, you may raise your hand and ask your question yourself. And you are most welcome to ask the questions in either Swedish or English, and we'll translate. Thank you.
Yeah. Hello. Okay. Yeah, my name is Andri, as was said, and today I'm gonna tell you a little bit about how stars bloom in our own galactic garden and beyond. So I've heard there's a lot of astronomers here tonight, but yeah, so this was made more for the general public, so yeah, bear with me, but yeah. Yes, so I start with the takeaways from this talk. Most of you probably already know that star formation is super cool and beautiful, but I want to convince you that studying star formation in the Milky Way is extra important, because then you can see the star formation up close. But that a lot of the Milky Way is still quite unknown, and that Gaia is very important in helping us see the bigger picture of our own galaxy. Yes, so I start with showing you a few of our galactic gardens, a few of the beautiful star-forming regions in our own galaxy. I start with this one, Westerlund 2. And in these gardens that I'll show you, you see a lot of beautiful detail and a lot of structure of how stars are forming. I'm also going to show you the Orion Nebula, which is the most nearby region where massive stars are forming, and the Rosette Nebula, also by the Hubble Space Telescope here. So you see that all of these are quite beautiful and quite different, and that they have a lot of strange structures that are in the process of forming stars. I'm also going to show you my favorite picture of a star-forming region, which is the Pillars of Creation. And they are so called because they are currently creating stars as we speak in these beautiful pillars. And we can zoom in on these to understand a bit more of what's happening. So in the top of this largest pillar, you can see these little pointy structures that we think are forming stars right now. And I'm going to show you what we think is happening inside of these with a picture that is actually from a different region, but we think that it's something similar here. So this is a protostellar disk picture taken by the ALMA telescope, which is in Chile. And in this protostellar disk picture, you see a protostar, a young star in the center, and then you see the rings around. And in these rings, we think that planets are forming in those rings. Yeah. Yeah, and we can also look at these pillars of creation in a different light. We can look at them with the James Webb Space Telescope. Let's see if this comes up. It's a bit big, this picture. Is it? Oh, okay. Okay. Maybe it went a bit quick there. Did you? Yeah, here it is. Yeah, so with the James Webb Telescope, we see even more beautiful structure in this region, and we see these kind of glowing areas in the centers of the pillars. These glowing red regions are regions where the gas is dense and heated a bit, where stars are in the process of forming. Yeah. So this is like a basic picture of how we think that stars form in the universe. We start with a giant ball of gas, which contracts due to gravity, and yeah, it gets strange structures because of turbulence and rotation. And then in the bottom of this picture, you see the protostellar disk, which is quite similar to the one that we saw in the picture from the ALMA telescope. And at the end, we get a stellar system like our own, with the star in the middle and planets around. And this is a very basic, quite nice illustration of how we think star formation works. But it has some problems because stars don't actually form alone. They normally form together in big groups. So it's not like one cloud becomes one star, but normally clouds become many stars. Yeah. And there's also turbulence and magnetic fields acting in this process. And yeah, so this is not completely how it happens. So I'm now going to show you a little simulation, which is a very nice illustration of how we think it happens. This video is made by Matthew Bates and collaborators at Exeter University. Yeah, so we start with this, it looks like a red ball, which is actually a spherical cloud of gas. And when we play this video, we see that this cloud starts to contract. There is turbulence in this simulation, which is part of the reason why it gets these structures. And we see that the yellow structures, which are the densest regions, start to develop. And after a little while, we get these little white balls, which are newly formed stars. And we see in this video that they definitely don't form alone. We get groups of stars forming together, and they're interacting due to gravity and evolving with the parent cloud. And we see maybe that this looks a little bit like some of the beautiful pictures that we saw in the beginning. And yeah, that it keeps developing and forming stars over time. Yeah, just gonna let it play here, and we're also gonna see this in 3D. So yeah, it's quite nice. This is a little bit more realistic than the picture that I showed you before, but also in this simulation, they have not included magnetic fields. And of course, a simulation can never really be as good as the reality, because we have, of course, limited resolution in time and space, and it's difficult to put all of the physical processes and all the scales in these simulations, even though they can give us a nice picture of what's going on. Yeah, so then I've showed you a little bit how we think that star formation happens, but what I haven't talked about yet is that these star forming regions are actually part of whole galaxies. So this is a picture of a spiral galaxy, the Whirlpool galaxy, and here you see this beautiful spiral structure with the spiral arms, and we see stars of different colors. All the light in this picture comes from stars. So the yellow light is from older stars, and the blue light is from younger stars. And then we see also these red regions of ionized gas around the spiral arms, and also these brown regions of that show molecular clouds or clouds with material for forming stars. So in this picture, we see that these clouds of gas, the red regions and the brown regions, follow the arms of the galaxy, and we also see that these blue younger stars also follow the arms of the galaxy, which means that the big scale size of the big scales in the galaxy have some effect on star formation. They also interact with the gas and makes it form more or less stars. So these scales are also important. And of course, we also live in a galaxy like this, so that all of the clouds that we looked at the beginning, they are a part of a big spiral galaxy, the Milky Way. And this is how the Milky Way looks from Earth. And yeah, we see some similarities. We see these brown cloudish parts, and we see some red regions, and we see stars of different colors. But the problem here is, of course, that we are inside the disk. We cannot see this spiral structure, and it's actually quite hard to decide the distances within this picture. It's difficult to know what part of the gas is in front of the rest. So it's hard to know the distance to the gas here. Yeah, so we have a kind of map of our own galaxy. So this is an artist impression of how we think that it might look, but it's actually not very accurate. We actually don't know how many arms the Milky Way has, how many spiral arms, or exactly where they are. So this map is actually, we're quite far from knowing this map accurately. So it's difficult to know where those beautiful star-forming regions that I started out with, exactly where they are in relation to all the arms, and how these arms are affecting the star formation in those regions. Yeah, so yeah, you might think it's easier to look at other galaxies because then you can see this this nice big spiral structure. But in other galaxies, the individual stars and the individual star-forming regions are way too small to see. So it's not possible to look at the same scales. So if you were looking at an individual star or an individual flower in our own galaxy, how big would it be if you put it in a different galaxy? It would be really way too small to see. We could compare it with looking at a single flower. And if we were to place this flower as far away as, when we look at this flower with our eyes, in order to compare it to looking at a single star in another galaxy, we would actually have to place it halfway to Mars. So it's like looking at stars in another galaxy is actually like looking at a tiny flower at the distance halfway to Mars. So it's really difficult to look at the small scales at large distances. Yeah, so this is like putting this flower 100 billion meters away. And yeah, this is not to scale. Yeah. So yeah, I already talked about that it's difficult to look at the small scales in other galaxies. And that is, of course, because the scale that we can look at changes with the distance. So, for example, when we look with the Hubble Space Telescope, which I've shown a lot of pictures from today, when we look at star-forming regions in our own galaxy, we can see, yeah, these nice star-forming regions. But when we look at other galaxies, the star-forming regions are just a few pixels, and we can see the large-scale structure. And when we look at faraway galaxies, the whole galaxies just become a few pixels. So we can see different things at different distances, but we want to try to combine all of these scales and all of these distances to understand the full range of sizes and how star formation is affected at all of these scales. And of course, as astronomers, we also know that when we look far away, we actually look back in time. And of course, how star formation has developed across time is also very interesting, but I'm not going to get into that today. Yeah, so some of the unknowns of star formation, which the community is working on, is how efficient is star formation, or how fast do stars form, and what decides how many stars we get and how big they become, and why is it only a small portion of the gas that end up becoming stars, and which of gravity, turbulence, and magnetic fields are most important at different scales and at different times, and what decides which stars gets planets and what planets they get, and which of them can get life, which, I mean, I think we will hear more about planets in the next talk. But yeah. So in order to try to solve these questions, it's interesting to look at the star-forming regions close to us, because then we can see the small-scale structure, but it's also important to look at the big-scale structure. And the best thing is to try to tie all of this together to get a full picture of what's going on. And that's a little bit what I tried to do in my PhD thesis, where I tried to collect all the as much information as possible about nearby star-forming regions and try to put them in their right place within the Milky Way disk. And this was only possible due to more accurate distances from the Gaia satellite, which is surveying the stars in the Milky Way, about 1 billion stars in the Milky Way, and getting very accurate distances. And this is actually going to improve the map we have of the Milky Way and the large-scale structure of our own galaxy a lot. So we're going to get a much nicer map of our own galaxy and a much better overview of the larger scale of our own galaxy with the data coming from this mission, together, of course, with understanding other galaxies and large scales with the other telescopes and other observations and studies. Yeah, so the takeaways from my talk is that star formation is super cool and beautiful on all scales, but that only in the Milky Way can you see it up close, but that the large-scale structure, the geometry of our own galaxy is still quite unknown, but that it will be much better known in the near future. So yeah, that's it for me, and I'm open for questions.
Thank you so much, Andri, for being here. So now we'll be moving on to the second speaker of the evening, which is Adam Rains, who is an astronomer based at Uppsala University, and will now be zooming in from the large galactic structures to something a little bit more close to home. So I'll pass the word on to you if you want to start sharing your screen.
Thank you very much, Lynn. That looks like it's sharing properly. Can everyone see that?
It is, thank you.
Great. So I'm going to, as Lynn said, do a bit of a zoom in. We're going to talk about planets in a bit more detail. I've got a lot that's, this is kind of a very high level overview I'm going to talk about, but then I've got a whole bunch of extra slides after my nominally final slide that goes into a bit more detail. So if you only have any more questions about detailed things, I probably have a slide about it. But just to begin with, who am I? So I don't hail from the Northern Hemisphere. I hail from the tropical part of Australia. So Swedish winters are a bit new to me. But what I do is I use the biggest telescopes in both Australia and in Chile to study stars that are redder in color, cooler in temperature than the sun. And I use their rainbows to do this, so their spectra. And I want to understand both the stars and the planets, because as we just heard, star formation is really complicated, and a lot can happen, and different kind of stars do it differently. And, you know, so that is definitely going to affect what kind of planets you can make. And planets are really small compared to their stars. So if we want to understand the planets, we really need to understand the stars. So I do a bit of both. My job currently at Uppsala University, I'm specifically trying to study the atmospheres of planets. And I've got a little bit of bonus content if you want to ask me questions about that later. So this is, we already heard mention of Gaia. So Gaia is an amazing space telescope. And what it's done is given us positions and, how bright, like 1 billion stars are in our galaxy. So this is kind of what Gaia has seen. And so remember, we're in our galaxy. And so it doesn't look like a spiral to us. We're kind of looking at it and it looks like kind of it's the Milky Way. It's kind of a bright strip across the sky. And we can see some dark, dusty regions here, which is where dust is. And we can see the brighter regions, that's towards the middle. And we can see these 2 other dots down to the over here. And these are external galaxies. They're the so-called large and the small Magellanic Clouds, which you can see from the southern hemisphere. So there's something like 300 billion stars in our galaxy. So that's 300 followed by 9 zeros, which is quite a lot. And if Gaia's told us information about, 1 billion, that's only a small fraction of the total stars, but it's a very good starting point to figure out what's going on. And there's at least as many planets in our galaxy as there are stars. And we've only found 5,000 of them. We've been doing good work. When I was born, we didn't know of really any planets. And in the last few decades, we've found more and more and more. In large part due to successful space missions like the Kepler Space Telescope. And now, Hubble has done a bunch, and you might have heard of JWST. It's doing even more amazing stuff. But there's a lot to learn about. But let's start close to home. So this is the solar system. And the sizes here are to scale, but the distances aren't. So the sun is really that big compared to Mercury. Jupiter's really that big compared to Neptune, etc. But they're not that close. Our night sky would look very different if they were that close. But a bit of a picture is painted here. So you've got the sun, you've got our 4 rocky planets, we've got an asteroid belt. We then have our 2 gas giants in Jupiter and Saturn, and they have a bunch of moons. Then we have our 2 ice giants. They also have some moons. And then we have the Kuiper belt. The Kuiper belt is kind of like an icy asteroid belt. And this kind of sets the picture for the solar system. And if we zoom in on this thing down the bottom, this is actually the distances spaced out to scale. So you've got the sun at one end, and all our rocky planets are really clustered together. Ceres is a dwarf planet in the asteroid belt, and I think it's about 1/4 of the mass of everything in the asteroid belt. And if you've, I guess, a fan of the science fiction series, either book or television, The Expanse, I think Ceres is spoken about a bit in that. But then we have Jupiter and Saturn, Uranus and Neptune. You can see the spacing gets a lot bigger, which is why it takes so long. Like it took us, Pluto's all the way here. It took us 10 years to send New Horizons from Earth to Pluto. This is why it's easier for us to get to the moon or to Mars than it is to send things to, to Jupiter or Saturn, or let alone Uranus or Neptune, which we've only ever flown by. We've never actually hung around there. And so when we think about the solar system, what do we have? We have Mercury, which is a rocky planet. It doesn't really have an atmosphere. We have Earth, which we're all hopefully quite familiar with. It has, it's rocky, but unlike Mercury, it has an atmosphere. Then we have Neptune, which is an ice giant. And so Neptune has a big atmosphere, but it's still there's still a lot of solid stuff inside it, deep inside it. This exact nature of it's a bit weird, but it's 20 to 30% gas, I think. And then we get to something like Jupiter, which is a lot bigger, and it's mostly atmosphere. So it's 90-something% hydrogen and helium. And so these are the kinds of planets we have in the solar system. And so, before we found any planets, we might have thought, okay, if we look around other stars, what are we going to find? Are we going to find these kind of planets? Are they going to be rocky close and then gassy further out? And so this is our solar system. All the distances here are to scale. And so we've got Mercury, Venus, Earth, Mars, and then out to Jupiter, and there's a big gap here. The asteroid belt's around here. And then we started to find planet systems, and they're all a bit weird. This is the first 51 Pegasi. So when star systems or stars get named, they're often named after constellations. So Pegasi is a constellation. And we've got this planet here was actually the first planet found around a sun-like star. And so you can see there's a star in the middle, and then in a few days, so really it's height in here, there's a Jupiter-like planet which goes around in a few days. And this is completely different than the solar system. In the solar system, Jupiter's out here, but in this system, Jupiter would be inside the orbit of Mercury. We also have another fancy system that was found more recently called TRAPPIST-1. In this planet, in this star system, there's 7 Earth-like planets that are, a little bit smaller than the Earth to a little bit bigger than the Earth. And all of them go around in about 20 days. So if you are on one of those planets, you get a birthday cake every 20 days or less. And so this is really a really amazing system to study. How did they get packed in so tightly? And then we have a even weirder system potentially called Kepler-47. And so both TRAPPIST-1 and 51 Peg, as well as the solar system, they only have 1 star each. But Kepler-47 has 2 stars. And then there are a bunch of planets that go around both stars. So that's completely different to what's going on in our own solar system. In our own solar system, we have 1 star, and the sun is kind of alone. The sun would have formed with friends back when it was forming, as Andri mentioned earlier. But now the sun is alone. But these Kepler-47, for instance, isn't alone anymore, or ever. It's got 2 stars that go around each other, and the planets go around it. If any of you have seen or remember the first Star Wars movie, the planet Tatooine actually is what we call a circumbinary planet. Because if you remember the scene, Luke is looking at the sunset, and there's 2 suns that are setting. And if you were around any of these planets, that's exactly what you would see. Some star systems are really big. So here we've got the outer solar system. So the inner planets are all condensed in here, but then we have Jupiter, Saturn, Uranus, Neptune, and Pluto. And this is a really stretched out solar system. And there are 4 planets that we know of in here, and they're all as big as Jupiter. And so imagine if there was another Jupiter that was out near where Pluto is. That's kind of what we're talking about here. And this star system is interesting. I'll touch on it a bit later. But it's quite a young system. And because these big planets are so far out, we've actually spotted them directly rather than indirectly like we do with a lot of planets. But these planets are still quite hot because they've only just come out of the oven, so to speak. And so that's kind of one of the ways that we look for them. But speaking more generally, how do we find these planets and what kind of techniques do we use? So there's lots of different kinds of telescopes. Turns out there's lots of different ways that you can, get glass and cameras together to make a telescope. And so we can use really big telescopes. This is the creatively named Very Large Telescope. It's in Chile. And so here there are 1, 2, 3, 4 telescopes that have mirrors that are 8 meters across. So that's a lot bigger mirror than you can buy in your typical hardware store. And this is one of the most, the fanciest and most scientifically useful observatories that we have on the planet. And it's run by an organization called ESO, the European Southern Observatory, where a bunch of European countries have gotten together, and they work together in conjunction with the Chilean government to have access to the southern skies. Because I mentioned before, there's stuff in the south you can't see from the north. So we need to build telescopes in the north and the south to see everything that's going on. We also use smaller telescopes, because one of the disadvantages of building a really big telescope is that everyone wants to use it. And so if you build a small telescope, and these can be as small as like cameras that you can buy, like DSLR cameras. So this is a network. It's the HAT South network, and it has telescopes that are in Chile, in Namibia, and in Australia. And these telescopes are pretty much DSLR cameras like you'd use if you were, a photographer. And they have big lenses on them. And because these are small, they're relatively cheap comparatively to buy and build. And you can use them for like a single university or a single researcher can have their own telescope and do what they want with it. And you also have space telescopes. And so there's, if we could, we'd put all our telescopes in space because it's on the ground. We've got to deal with weather. I was just the other day actually using these telescopes remotely. So I was connected via computer using them. And towards the end of the night, we started getting clouds rolling in. And so we couldn't really observe what we wanted to. But in space, there's no clouds that get in our way, like a rain that happens on Earth. And that makes it a lot nicer to observe with. But the challenge is that space is really challenging to put things in. And space is a really foreign and difficult environment. So like some of you might remember or have heard of when the Hubble Space Telescope first launched, it had a problem with its mirror. And essentially we needed to go up and put glasses or a monocle, as it were, on Hubble to upgrade it. And that was done with the space shuttle. And that was really complicated to do. It's much easier to just drive a truck to one of these observatories and fix it if you need to. But over the years, we've had a lot of telescopes in space. So Hubble is probably the most famous. Now we have JWST, which you can think of as a replacement for Hubble, which observes in the infrared. So that's the light that, say, security cameras use or night vision goggles. And you can't really observe in the infrared light from the ground because our atmosphere blocks it. And then you've got Kepler and TESS, which have done a lot of great planet work discovering planets. But as for some of the techniques we use, the technique that's discovered the most planets is called the transit method. And so here we're watching a video of the transit of Venus in 2012. And so in a transit, a planet blocks some of the light from its host star. And so from Earth, what we're seeing is Venus crossing the surface of the sun from our perspective. And you can see the light before the transit is at 100%. We're getting 100% of the light from the sun. And then as Venus enters across the sun, that light drops down. And it drops the light that we're getting from the sun by 0.08%. So that's a pretty small number. But if we have sensitive enough telescopes, we can detect it. And different planets will block different amounts of light. So a planet like Jupiter might block 1% of the light around a star, whereas Venus is blocking, 0.08, and Mercury or Pluto would block even less. And so what we do to find planets with this method is we basically just stare at a patch of sky for as long as possible. So for instance, Earth has an orbit of 365 days. And so if you were lined up just right out around another star looking at Earth or the sun, you would see Earth block some light, and then you'd have to wait another year for Earth to come and block the light again, because you want to see it happen multiple times, because if it just happens once, you don't know if it was a planet that's actually orbiting the star, or maybe something just went past, or maybe it was something like a spot on the star, like the sunspots that happen on the sun. And also, so this is why this method tends to find planets that are quite close to their stars, because we can catch repeat observations more quickly. Whereas if you wanted to observe Jupiter, you'd have to wait like 12 years, I think, between Jupiter transiting the sun. Another method, which made the first discovery, so that was the 51 peg discovery, is the so-called wobble method or radial velocity method if you're in the field. So what this is, so when stars are really small compared to their planets, but they're still big and they still have gravity. Anything that has mass, anything that's made of atoms has gravity. And so what's actually happening is that the planet isn't orbiting the star. The star and the planet are actually orbiting their common center of mass. So if you imagine like linking hands with someone and like spinning around in a circle, you're spinning around a point between you. And if you do that with an adult, or if you do that with like a child, you're spinning around different points. Like if you're spinning around something much smaller than you, like with a child, the child's going to be spinning around you. But if you pick someone your size and spin around, you're spinning around a point between you. But what this means is that even the smallest planet is still going to make its star do a little bit of a wobble. And there's this, you might have heard of something called the Doppler effect before. If you've ever heard, say, a fire truck or a train go past, and it makes a different sound when it's coming towards you versus when it's going away from you. That's because of the so-called Doppler shift of light, Doppler shift. And that happens with sound, but Doppler shift also happens with light. And so what we're seeing here is the rainbow of the star is shifting back and forth depending on where the star is in its little wobble. And a star's spectrum, a star's rainbow, kind of looks like a barcode because of all the elements and atoms that are absorbing light in the star. And so you can see this barcode shifting back and forth. And from that, you can work out that there might actually be a planet there. And so that's quite helpful. And those first two methods are comparatively easy compared to this one. This one is quite tricky. So this is the star system I spoke to you about earlier, the baby star system that has the 4 Jupiter-like planets. And why it's tricky is that stars are really bright and planets are really faint. So it'd be like saying, trying to see a planet is kind of like trying to see a firefly next to a lighthouse. Sure, the firefly is glowing, but the lighthouse is glowing a lot more. And so when you want to see a planet directly, the best way to do it is to either have your planets far away from the star. So imagine if the firefly was further away from the lighthouse, or if your fireflies were brighter. So it's going to be easy to find brighter fireflies. And this is why we look for baby planets, because they're kind of glowing because they're hot out of the oven. They've just been born. And so that's why we often find big young planets in these like the Orion Nebula or places like that, where there's lots of baby stars with this method. And we can even, so those planets have already been made. These planets are still in the oven. So this is a system called PDS-70. And so this here is an image taken in the optical and near infrared light. So the light we can see with our eyes and light that's a little bit redder of this planet that's being born. And this is what this system looks like in the radio. So the radio, you know, we can't see with our eyes. It's kind of what like Wi-Fi is doing. But astronomers look in multiple different wavelengths at once or separately, but it tells us different information. So looking in the radio here is telling us what the gas is doing, whereas looking in the optical and IR is telling us what the dust is doing. And the star's in the middle here and it's been blocked out. But that's basically a summary of some of the most common methods that we use to find planets. And really, it's not what we expected. Like, we might have thought that we were going to find a whole bunch of other solar systems out there, but everything's a lot stranger. And we can't go back in time and see what the solar system looks like when it was young, but we can look at nearby stars that are young and making planets and see what their planets look like and say, you know, maybe that's what the solar system is like. But it's a very exciting time. We're still discovering a lot of planets, and, you know, might well be within our lifetimes as we build more and more telescopes and look at more and more planets that we keep working on studying their atmospheres and maybe find something in their atmosphere that might be could only be produced by life. That'd be really exciting. But as I said, I've got a lot more backups or extra slides if you want to hear any more detail about what I've discussed. But thanks all for listening.
Thank you so much, Adam. Round of applause for you.